Hi everybody, I happen to be posting this video to my YouTube channel on my birthday. Please, no singing. Have you ever met somebody that has the same birthday as you? It's kind of surprising when that happens, right? Well, I happen to know somebody really well that has the same birthday as me. It's one of my brothers. And no, we are not twins. This is a photo of me and my siblings in our birth order from left to right. I am the oldest and heir to the O'Connell throne. Then comes my sister Joanne, my brother Brian, and our youngest brother Brendan. And it turns out that Brian and I are exactly 4 years apart in age. We have the same birthday. And this seems like a great introduction into what is called the birthday problem. Given a group of n people, what is the probability that at least 2 of them have the same birthday? And we're going to assume that these birthdays are what we call independent, meaning there's no sets of twins, but also there's no other factor that might make one birthday have a higher probability or lower probability than any other birthday. And to that end, we're going to ignore February 29th as a birthday. Please, no offense to those of you that have that as a birthday. It's just that when we consider that, it makes the problem significantly more complicated and only a little bit different. So ignoring that is going to give us a really good approximation as to the answer. All right, so let's look at my family. What is the probability that when you've got 4 people, 2 of them have the same birthday? When you have a group of 4 people, we need to list out what are all the possible outcomes that could happen. We could have none of the people having the same birthday. We could have that 2 of them are the same, as was the case in my family. Could have 3 of them being the same, or 4 of them being the same. And lastly, we could have that there are 2 pairs of 2. Now, if we group all of these outcomes together, those all satisfy the at least 2 are the same condition. And now we can see that the probability of at least 2 of them being the same is going to be 1 minus the probability that none of them are the same. So now the question has come down to, what is the probability that none of the 4 people have the same birthday? When I look at this problem, I like to think of it as each of the people having a choice as to what their birthday is. And yes, I do know how birthdays work. We don't have a choice about that, but it gives us the correct answer, and it just is easier for this brain to think about it in that way. So now to find the probability that none of the 4 people have the same birthday, I'm going to assume that all 4 people have 365 choices for birthdays. The first person gets to choose any birthday that they want because there's nothing to avoid. But the second person now has to avoid the first person's birthday, which means they have a choice of 364 birthdays. Similarly, the third one is going to have to avoid the previous 2 birthdays, so they have a choice of 363, and then the last one gets a choice of 362 for the same reason. My calculator tells me that this is about 0.9836, which means there's a slightly better than 98% probability that none of the 4 people have the same birthday. That is an incredibly likely event, and I think that matches what our experience would tell us. But it means that the probability of at least 2 of them having the same birthday is 1 minus this probability, or about 1.64%, which turns out to be about 1 in 60. Now, the thing that amazes me about this 1 in 60-ish number is not how small the number is, but how big the number is. Yes, still a relatively small probability, so we are surprised when this happens, but that probability is not as small as we would think it would be when we are approaching this problem. And I also have to say that that number feels about right to me. My brother and I are good friends. We have friends in common. We often spend our birthday together. And the fact that we have the same birthday, it will come up in conversation. And the vast majority of the time, people will be surprised. But on a fairly regular basis, people will tell us that something similar happened in their family. My wife has a sister who's got the same birthday as their dad. We will fairly regularly hear, oh, I've got the same birthday as my cousin, or my birthday is the day after my mom's. Is this probability something that is going to surprise us? Yes, it is. But is this as unlikely as we would think? Absolutely not. And these probabilities only get more surprising as the number of people increases. Hopefully you can see that the way that we would figure out the probability for 10 or 15 people is to just attach more fractions onto that probability of none and then subtract that from 1. This table and graph show how surprising these probabilities are. By the time you get to 10 people, it's almost a 12% chance that at least 2 of them have the same birthday. And something absolutely amazing happens when we hit 23 people, because that's when the probability jumps above 50%. This means that anytime you're in a group and there's at least 23 people, it is more likely than not that at least 2 of them have the same birthday. That is an absolutely stunning result. And we can see that 26 people gives us a probability of around 60%, and I'm going to use that fact in a moment. And then by the time we get to 50 people, it is an almost guaranteed probability that at least 2 of them are going to have the same birthday. So I decided to look for a real-life set of data where we could try to verify these numbers. And what I came up with was rosters of Major League Baseball teams. Now, a couple things. Major League Baseball team during the regular season has an active roster of 26 players. Might be 27 if they have a doubleheader, might be 25 depending upon what their injury reserve looks like, but 26 is a pretty solid number. And also, the players on an active roster can fluctuate throughout the year with people going on injury reserve or being called up or sent down to the minor leagues. So on June 17th, 2026, I went to MLB.com and copied and pasted the rosters of all 30 of the Major League Baseball teams, which included the birth dates of all the players. We found on the table that if you've got a group of 26 people, the probability is about 60%. So I should find that about 60% of the Major League Baseball teams have at least 2 players with the same birthday. There are 30 baseball teams. 60% of 30 is 18, so I'm looking for about 18 of the teams to have at least 2 players with the same birthday. The data absolutely blew me away. You can find a link to my spreadsheet in the comments below. Turns out that 20 of the 30 teams had at least 2 players with the same birthday, which I think is pretty close to the 18 that we were expecting. 14 of those 20 teams had 2 players with the same birthday. 5 teams had 2 pairs of birthdays that were the same. And the Cincinnati Reds have 3 pairs of players that have the same birthday. And how could it get better, you ask? Well, it turns out that the Blue Jays and the Cincinnati Reds each had a pair of players with not only the same birthday, but also the year that they were born was the same. The birthday problem is an extraordinary result that never ceases to amaze me. Hey, I hope that you enjoyed this video. If you did, feel free to subscribe below or not. I don't really care. I don't make videos to get more subscribers. I make videos about math that makes me happy, and the birthday problem is math that makes me happy. Again, I hope that you enjoyed this video, and I will see you in the next... Oh my gosh, I have to call my brother. It is his birthday. What's up, brother? Happy birthday! I know, right? I was just making a video about it.